Good afternoon.
Good afternoon, Lashi.
Good afternoon, Oshi.
So, today we're gonna talk about the differential, which is very similar idea of the derivatives. And if you couldn't fully understand the definitions, don't worry. I will mention what you need to remember or what you will use in the future for this part. So let's start. Okay. So as usual, we're gonna give the definition of differential and talk about the relationship between differential and derivatives and some properties and maybe some applications, which is not really important, but the relation between differential and derivative, you have to be really careful about that. Okay, as usual, I gave you an introduction, just a taste of the differential. So given a metal disk with radiums R, and if we increase the radiums as by delta R, so from R to R plus delta R. So the question is, what about the increasement of the area of this disk? So we know the area formula is, the area of this disk is pi r to the power of 2. And so the increasement of the area is pi multiplied with the new radiums minus pi multiplied with the pi r square. And you do the calculation, you get this one. So if you look at this formula, you will see this formula being divided into two parts. The first part is some kind of constant multiplied with delta r. Why I say this is kind of constant? So you can actually, if you think this is like r is a random variable. So this part is related to r, but not related to delta r, not related to the increasement. And this part is pi multiplied with the delta r to the power of 2. So you can see when delta r goes to 0, this one goes to 0 faster than this one. And it's really, really fast. And so in this way, we call this is the linear part of delta A, because you treat this one is not related to delta R. This kind of constant multiply with delta R, and this is a very higher order infinite small of delta R. And also we call this is this is the main part. This is the main part of the increasement of A. And this part is the higher order infinite small of delta R. This is also called the negligible part of the increasement of A. So when this is in small enough, the increasement of the function is locally linear approximated by 2 pi r delta pi, because I said that when delta r goes to 0, the total increasement, this part will vanish very fast. Okay, so we said we can use the main part to approximate the increasement of A. Now we have the definition of the differential functions. Suppose y is has a domain I, which is an interval. I is an interval. And suppose that x0 and x0 plus delta x are both in the interval. So from x0 to x0 plus delta x, they are both stayed in I in the domain of the function. And the increment of f, you can calculate this. If the increment of f can be divided into two parts. The first part has nothing, is a multiplied with delta x. Here I said a is a constant. That means a does not depend on delta x, but it might depends on x0. So it's kind of something related to x0, but not delta x. Okay, a is not depends on delta x, and another part is a higher order infinite small of delta x. Then if f, the increment of f can be divided into two parts like this, then we call f is differentiable at x0, and the linear function from delta x into a multiplied with delta x is a differential of f at point x0. So this is the differential is of a function is another function. A function has, you can treat it as a function with variable delta x. We can denote it by df x0 or dy. So the differential is a linear function, but the linear means does not, because this you can treat this as a function of delta x. So a is not related to delta x, but related to x0, okay? And these two, delta y and dy, are different concepts. Delta y is the accurate increment of the function, okay? But dy is a linear function with independent variable delta x. And this is also rise from the main part of the increment of the function. And this is their relation. So this is a relation between the differential of y and the increment of y. Okay, this is a relation. So the question is, how do we find the differential part? When I give you a function like that, is there an easy way to find it? Because when you calculate, like if you calculate by the definition, that kind of be a huge, if the function just slightly very complex function, then you have to do a lot of basic calculations. That kind of be horrible. That will be horrible. And you can do this. You can just, for these simple functions, you can treat them like this by the definition. And then you know the differential of this function is just a function from delta x to delta x. So this is actually just the df is equal to delta x, okay? And if f is just a polynomial, a very simple polynomial, what's the differential? You do the calculation by the definition, then you know this is from delta x to a multiplied with delta x. And then you see, so what we need is actually the main part of the increment, which is, and to be more precisely, we need to know the constant a, the capital A in the previous slides. So if you look at these two exams, you know this is 1 multiplied with delta x, and this is a multiplied with delta x. And if you remember, the derivative of this function is 1. The derivative of this function is a, right? So now you can guess what's the relationship between the differential and the derivatives. Okay, let's see. First of all, I need to tell you that if the function is derivable at x0, if and only if f is differentiable at x0, if you still remember, if f is differential at x0, then we know the increment of the function will be written into two parts. First part is some constant multiplied with delta a. Hereby constant a is not, it means it does not depend on delta x, but it might depend on x0, okay? And multiply with a plus a negligible part of this increment. So this is the differential function from delta x into a multiplied with delta x. This is differential. And so if you divide the delta x on both sides, then you let delta x goes to 0. What is that? This is a definition of the derivative, the derivative of the function at x0, right? So now this gives you a hint that in this proof, the differential is at x0, the differential of f at x0 is the derivative of f multiplied with delta x. Okay, this is very simple. So on the other side, you start with f is derivable at x0, then you know it can be written like this. And then you do the calculation. Everything is just similar. And so now you know the what is that? Now you know how to calculate the differential of a function at some point. You just calculate derivative and write it like this. Okay. Okay. So for example, if I'm asking to find the differential of a function x to the power of 2 at some point, then you just calculate derivative of this function, which is 2x, right? So the differential of x to the power of 2 is 2x multiplied with dx, okay? Okay, it's quite simple. And then you can see from this, if I give you a differential of the function, then you can easily get the derivative of the function. So this is a one-to-one mapping, okay? And what is the difference now? What is the relationship between differentiable and derivable and continuous and limits? It's just simple. A derivable if and only means differentiable, and both of them can imply continuous, and continuous means the limit exists and equal to the value of the function. And this is just some graph. You can try to rate it by yourself. So this is a differential function, and this is the function. This is the most important theorem you have to remember. And we're gonna use this a lot in for the integrable part in our calculate lectures. So when f is differentiable at x, then the differential function is equal to f prime multiplied with dx. So now can you tell me the answer of this one? What's the differential of e to the power of x? What? No, it's not dE. Yes, it is e to the power of x multiplied with dx. Don't forget about the dx, okay? Yes. And how about this one? Sine x, the differential function of sine x. Correct. It is cosine x multiplied with dx. And ln x will be x over x dx. Okay, so everything is just like before, but you write it in different way. And now we have some calculations for that. It's also like you can prove from the calculation from of the derivatives. So differential of f plus g is equal to the differential of f plus the differential of g. And the multiplication of two functions as you roll like this. And now f divided g is like that. Everything is similar. And now can you try to find this one? The differential of, yeah, differential of f. Okay, so the answer is ln x plus 1 dx. So you just find the derivative of f and multiply with dx. And then you do this in two ways, okay? For the solution 2 is actually using this formula. You can see it's much easier than that one. Okay, and the differential of composition of functions is still like you just calculated the derivatives. You just calculated the derivative, then you just multiply with the dt. And then you do the, and then just try to find this one. Yes, correct. So the answer, you can just try to find the derivative of this guy, which is just like that. So the derivative of that, the derivative of e to the power of something, and multiply with the derivative of that something, okay? And now the other important, why we talk about differentials, that will give a very simple solution for the implicit functions. For example, if the equation x to the power x equal to y to the power of y, so in this way, this equation can decide the function y and the independent of independent variable is x. And now I'm asking to find the differential of y and the derivative of y related respect to dx. What we should do, we just do the differential. We first take the logarithm on both sides of this equation, and then we get this guy. And then we take in the differential on both sides, then we get this one. So you take the differential on this side relate to x, you will get 1 1 over x dx, and you take a differential on this side for y, you will get ln y and dy and the plus dy. Okay, so this is, you just find the derivative of this guy related to y, and then you multiply with dy. This will give you the differential of the function on this side. And then you just make the solution for easy equations. So then you get dy is equal to, so just like that. You put them together, you put this together. So this part is ln y plus 1 and dy. Okay, and then you divided the dx on both sides, then you cancel this guy, then you get dx here. And then you move this guy on this side. Then then you will get this formula. Okay, so this is the answer you want. And this is the very useful technique for finding derivatives. Suppose this is one of the exercise for today, and it's gonna be in your homework. And so another exercise is now I'm giving you the differential functions. I'm asking you to find the original function. For example, sine x dx is equal to the negative cosine x and differential of the negative cosine x. And 5 multiplied with x squared dx, the original function, this is the differential of 5 over 3 x to the power of 3. And for this guy, it's a little bit hard. It's gonna be 1 over 2, and you just make the regular calculation. You just make it like something you know, like you're familiar with. And then you know something like 1 over 1 plus x to a to the power of 2 is the derivative of arcotangent x. So you just make the solution like that. And for this guy, you already know which is x ln x, and so on. And this part we don't need to know. And this is another exercise for today. No, this is not the exercise for today. I'm sorry, but I will give you the exercise in the group. And okay, then that's it for today. And so things are just very similar, but you have to remember this guy. This one. Where is? Here. Sorry. You have to remember the important theorem. This one, that one. This one. We don't have to learn the linear approximant at 0. So someone was asking. And if you are interested, you can just read my slides and try to learn by yourself. And this is the important thing for today. If f is differentiable at x, then the differential of f is equal to f prime dx. And for this is gonna be very important for the future, and for the like the implicit finding the derivative of implicit functions. Because this way, this is something very important for the integrable functions and for the integrals. And next, let me see. Next lecture, we will start the oh no, we still need to learn I haven't told you about the low hospital rule, right? I haven't. So
No, 老师.
Next week we're gonna talk about the low hospital rule. We just give you some useful technique for the calculations. And we also need to learn the monotonicity and the extreme value of some functions. And then we finally go to integrals. Okay, then I hope this gonna be. Wait a little bit. Let me see. Should we wait? Wait. Oh. Maybe I can find some. Oh no. Okay, then that's it. That's it for today. Then yeah, I will send the slides and also the homework. Then okay.
OK，老师，谢谢
You're
你。
welcome.